So now we're going to determine discontinuities in algebraic representations of functions. So this is what we're going to do without the graph first, and then we're going to graph the functions to determine what type of discontinuity this is. Now we've already gone over the three different things that are going to make a function discontinuous at the point. Number one, if f of a is undefined. Number two, if the limit as x approaches a of f of x does not exist. And number three, if the limit of f of x as x approaches a does not equal f of a. Now let's be more specific about how exactly f of a can be undefined algebraically. So we're going to talk about the things that make a function undefined. So a function is undefined when we have a few different things. Number one, a function is undefined when we have a 0 in the denominator. Number two, a function is undefined if we have a negative inside of a square root, or really any even root, so a fourth root, a sixth root, an eighth root, etc. So a negative inside of an even root. And finally, when we're dealing with logarithms or natural logarithms, when we have 0 or a negative inside of a logarithm. Now, there are a few more things that are going to make a function undefined, but this is really what we're going to see today. And so let's go ahead and start with a. We have f of x is equal to x squared minus x minus 2 divided by x minus 2. Now, because this is just a function, this is not a piecewise function, we're not really going to be worried about the limits. Because if this is continuous, then the limit of this function at any value a is just going to equal f of a. And so let's just figure out, based on these three different things, if this function is discontinuous anywhere by figuring out if it's undefined anywhere. So, can we get a 0 in the denominator? Well, yes, we have a denominator. How do we get a 0 in this denominator? Well, I'm going to set the denominator equal to 0. Where does x minus 2 equal 0? At x equals 2. And so there's going to be some type of discontinuity at x equals 2. Let's keep going because there can be multiple discontinuities. So can we get a negative inside of an even root? No, we don't have an even root. Can we get a 0 or negative inside of a logarithm here? No, we don't see a logarithm. So we only have one discontinuity at x equals 2. Part B, we have g of x equals 1 over x squared if x is not equal to 0. G of x is equal to 1 if x equals 0. So this is a piecewise function. When we have piecewise functions, we are going to worry about our limits. So we want to make sure all of these three things are true for any value of a. So let's start off with f of a being defined at any value. So I know that g, and in this case my function is g, I know that g of 1 is just 0. Can 1 over x squared be undefined anywhere? Yes, 1 over x squared is undefined at what value will give us a 0 in the denominator? 0. It's undefined at x equals 0. But this is where the second piece of this function comes in. I already have that g of 0 is equal to 1. If x equals 0, g of x is equal to 1. So g of 0 is equal to 1, which is defined. In other words, This function is defined for all values of x because it has the value of 1 over x squared for any value of x except at x equals 0 where it has the value of 1. So this is defined everywhere. Next, I want to make sure the limit of g of x at all values exists. So, does the limit of g of x at all values exist? Let me look at this 1 over x squared. What value might make this not exist? Well, that's going to be the limit of 1 over x squared as x approaches 0. Because I know that when I'm finding limits, if I plug in 0, I get 1 over 0. And whenever I get a constant over 0, I know this is going to be some type of infinity. And let's remember that when we have a limit of positive infinity or negative infinity, all we're really saying is we're really telling you what type of undefined it is. So the limit does not exist for any type of infinity, but infinity just tells you, okay, this limit doesn't exist, but in what direction? And so if our limit does not exist, then we're breaking rule number 2. And so we have a discontinuity at x equals 0 because the limit at x equals 0 does not exist. So our discontinuity will occur at x equals 0. Next, h of x is equal to, this is another piecewise function, x squared minus x minus 2 divided by x minus 2 if x is not equal to 2. And if x is equal to 2, this function is equal to 1. So starting off, to determine where this function is undefined, so x squared minus x minus 2 over x minus 2 is undefined. Well, this is the exact same function from part A. This is undefined at x equals 2 because this is going to give us a 0 in the denominator. This is a 2 at x equals 2. But we have that h of 2 is 1. What this means is that this function is defined for all values of x. So first requirement is met. The second requirement is that the limit exists for all values of x. So where do we think this limit might not exist? Well, at 2, which will give us a denominator of 2. So let's see if we can find the limit as x approaches 2 of this function. Now immediately, if we plug in x equals 2, what happens? I get 2 squared, which is 4, minus 2, minus 2. Okay, now I have a 0 in the numerator and a 0 in the denominator. This doesn't mean my limit doesn't exist, it just means I don't know what my limit is yet. If I get 0 over 0, I'm going to try to do what we've been calling remove the discontinuity, using my techniques of factoring, rationalizing, or some of those other miscellaneous techniques. I see a numerator that can likely be factored, and so I'm going to try to factor this numerator. I'm going to say that x squared minus x minus 2 over x minus 2 can be written as, I'm going to break this up into 2 factors. Since this is a trinomial, the first term in each of my factors is going to be x, and then I'm looking for 2 numbers that multiply to give me negative 2 and add to give me negative 1, and those numbers are negative 2 and positive 1. With my denominator of x minus 2, now I can cancel out this factor of x minus 2 in the numerator and the denominator. And so, can I find the limit as x approaches 2 of x plus 1? Yes. Now if I plug in 2, this is going to give me 2 plus 1, which is 3. And so finally, I just want to make sure that the limit of this function as x approaches 2 is equal to the actual value of this function, where x is equal to 2. So I saw that the limit, instead of writing out this function as x approaches 2, I'm just going to write that out as h of x. The limit as x approaches 2 of h of x we just found is 3. This is not equal to 1. This is not equal to h of 2, which is equal to 1. Because the limit as x approaches 2 of h of x does not equal h of 2, then I can say that there is again a discontinuity at x equals 2. And we'll see the difference between these two things graphically. Up here in part B, we found out that the limit doesn't exist. For some value of x, here the limit exists, but it doesn't equal the actual value of that function at the point. Finally, for part D. Part D is just a function, not a piecewise function. And so let's look back at what we have written up here. So this is undefined when we have a 0 in the denominator. Well, we don't have a denominator. When we have a negative inside of an even root, I don't see any even roots. And when I have a 0 or a negative inside of a logarithm. Well, maybe I can get a negative or a 0 inside of this logarithm. Let me find out where 1 plus the cosine of x is less than or equal to 0. That's really what I want to find if I want to find a negative or a 0 inside of a natural logarithm. So solving this inequality, let me bring this 1 to the other side, and I get that cosine of x is less than or equal to negative 1. Now, I know that cosine is between negative 1 and positive 1, so cosine of x can never be less than negative 1, but because of this less than or equal to, cosine of x can be equal to negative 1. Now, where does that occur? Sometimes I like to draw my unit circle, because on the unit circle, the cosine is just the x value of each of these points. Cosine is negative 1 right here. So this is pi, but this value is the same as 3 pi, which is the same as 5 pi, which is the same as 7 pi. Because I have infinitely many x values that are going to give me a cosine of negative 1, meaning I'm going to have a function that is undefined, I'm going to describe it using this n notation. So let's make note that this function is undefined when the cosine of x equals negative 1, which occurs at x equals pi, 3 pi, 5 pi, etc. So how can I describe this with this integer n? So if I want n to be an integer, I'm going to let n be an integer. I want to say that I have a discontinuity where x is equal to an odd integer times pi. I can describe an odd integer using 2n plus 1. Because if n is an integer, starting at 0, my first x value will be 1. Next, if n is equal to 1, the next integer, my x value is 3. If n is equal to 2, my next x value is 5. So using 2n plus 1 just gives me the odd number integers times pi. So this is how I can describe where these discontinuities occur. So next, we want to graph all of these functions to determine the type of discontinuity. If I graph this first function, x squared minus x minus 2 divided by x minus 2. And I go to a standard window. This looks like a straight line, but I see this discontinuity at x equals 2, so I'm going to go to second trace, press enter, and actually find out the value of x equals 2. Just to ensure that there's an error here or a blank, which means that what there really is there's a hole at x equals 2 that I can't see on the graph. And so this graph is going to look something like this. This is a line that's shifted 2 units up. And at x equals 2, I've got a hole right here. So this is the graph of my function. Now, what type of discontinuity is this? Let's look back at my types of discontinuities. I've got removable, where I've just got a hole. I've got jump, where this function is jumping, and then I've got infinite, which means I have an asymptote. Because I've just got a hole, this is a removable discontinuity. So next, I've got a piecewise function. Now to graph this piecewise function, if I want to use my calculator, I can't quite graph the pieces, but I can in my head know that g of 0 is 1. So I know what that point looks like. It looks like a point at 0, 1. So let me keep that in mind as I graph this first function of 1 divided by x squared. One divided by x squared is going to look something like this. Here I see an asymptote along the y-axis. So let me do a rough sketch of this. Very rough sketch here. Now, this is true everywhere where x does not equal 0, but when x equals 0, g of x is 1. So I've really got this point right here at 0, 1. What type of discontinuity occurs at x equals 0? Well, you might be tempted to think that it's a jump discontinuity because of this point, but I also have an asymptote, and so I can say that this is an infinite discontinuity. Next, part C, and again, I'm just going to graph this first function. And didn't I already graph this function? I graphed it right up here, so we actually don't even need our calculators for this. Let's graph this, and I'll graph it. Let's try to fit it in right down here. So I know that this is going to be exactly the same as up here everywhere except for x equals 2. So I'm still going to have this be a line with a hole at x equals 2. The only difference in part C is that now when x equals 2, I have that h of x is equal to 1. H of x is equal to 1. So I've got a point right about here. This still is a removable discontinuity, because I could fix the problem by redefining h of 2 as 3. That would fix the problem. Finally, I have the natural log of 1 plus the cosine of x, and this one's kind of interesting. We said that there's a discontinuity at all odd values times pi, so let's see what this looks like. We've got the natural log of 1 plus the cosine of x. And let me make sure I have both of my parentheses. Let me adjust my window a little bit. I want my x max, and I want these tick marks to be in terms of pi. So let me make this negative 5 pi. And let me make my x max 5 pi. and then have my x scale at pi so that I see all of these tick marks along at pi. And so let me see what happens here. Now, while it doesn't quite show it on the graph, I have a series of asymptotes, and I can see that they occur at odd values of pi. Because of how I set my scale, I've got 1 pi, 2 pi, 3 pi I've got an asymptote, 4 pi, and 5 pi I've got an asymptote, and same thing in the negative direction. And I'm going to do my best to sketch this graph. Something like this, where I've got 1, 2, 3 to make sure my asymptotes are on odd values. Okay, this is a general idea of what this looks like. I can see that this is also an infinite type of discontinuity because of those asymptotes. All right, now let's try to do one more type of problem. It's kind of like a little puzzle. I want to know for what value of the constant c is the function f continuous on negative infinity to positive infinity. So first, if I'm looking at c as these random constants, no matter what c is, can I see that this function is going to be defined on the interval from negative infinity to positive infinity? The reason I can say that is because there aren't any even roots, there aren't any natural logarithms or logarithms in general, and there aren't any denominators. And so all I really need to be concerned about is what's happening at x equals 2 when I switch over functions. Because I know that if f is to be continuous on this entire interval, the limit as x approaches 2 of c x squared plus 2x must be equal to the limit as x approaches 2 of x cubed minus cx. Another way I can write this is that the left-hand limit, which I'm going to take from cx squared plus 2x, must be equal to the right-hand limit, which I'm going to take from x cubed minus cx. So I can show that this would be the left-hand limit and this would be the right-hand limit. Now, because there are no x values that are going to make each of these functions on their own discontinuous, because we said we don't have a 0 in the denominator, we can't get any kind of negative or 0 in a logarithm, we can't have a negative inside of an even root. Because that's true, I know that I'm going to find these limits by just directly plugging this value of a into this function. And so now I can say that when I plug in this 2 from the left into my function, I'll get something that looks like c times 2 squared plus 2 times 2. On the right, when I have this limit as x approaches 2 from the right, again, I'm plugging in 2, and I get 2 cubed minus c times 2. Now I'm just solving this equation for c. These c values are going to make this a true statement. 2 squared is 4, and I get 4c plus 4 is equal to 8 minus 2c. Now I've just got a linear function, so I'm going to get my c's on one side of the equation and my constants on the other. Adding 2c to both sides, I get that 6c plus 4 is equal to 8. And subtracting 4 from both sides, I get that 6c is equal to 4. Finally, dividing by 6, I get that c is equal to 4/6. And I always want to simplify fractions. So finally, I can say that c is equal to 2/3. So a c of 2/3 is going to allow this function to be continuous on the interval from negative infinity to positive infinity. And the reason for this is that this c value is going to give us the same left-hand and right-hand limits where this piecewise function splits.